Hey students, today I'm going to talk a little bit about density. So density is a measurement. It's actually a ratio or a conversion factor of different measurements put into a quotient or a relationship. So a lot of times people are mistaken and they say density is how heavy something is. And that's really not true. You could have 100 pounds of feathers, just like you could have 100 pounds of gold. The difference is the amount of space they would occupy. So you could think of density maybe as relative heaviness. So if you've ever felt a gold or silver coin, they're far more dense than the coins that are circulated today. Another way of thinking of density is what I like to tell students is the proximity of the particles to one another. How close is everything packed? How tightly packed is everything? And obviously, we're always going to use water as a comparison. Does it float? So we see that this cork here floats on water. Why? It's less dense. We see that these metals, they tend to sink in water. Why? They're more dense, they're more tightly packed. So density is actually the combination of two measurements. It's a mass measurement divided by its volume measurement. So it's kind of like, speed or rate or velocity. That is distance over time. So you could have miles per hour, meters per second. It's still distance over time, and that is rate. So that is a type of measurement. It's a combined measurement of two different types in a ratio, and that's what density is. So what is density? Mass over volume. And yes, it's a formula, and you should memorize it. It's a pretty easy one. I always tell students, you can just think of the DMV. Density is mass over volume. DMV. It's pretty straightforward. It's pretty simple. So it basically compares the mass of an object to its volume. So the mass of the substance is just divided by its volume. And you basically get this quotient. Typical units are grams per milliliters or grams per centimeter cubed. Again, you could have pounds per liter. But in a science lab, we're not really measuring pounds and we're not typically measuring liters. Grams and milliliters are more common. And remember, 1 milliliter is equivalent to 1 centimeter cubed. Remember, I said 1 cc. You can think of it as if I had a perfect cube and it measured 1 centimeter by 1 centimeter by 1 centimeter, and I poured water in it, that would be 1 milliliter. So again, you should know that those are used interchangeably. So here I have a table of different substances and their densities. So if we take a look at the solids, we see that the density unit is grams per mil. And there's a wider range of densities. And we can see that some of the metals definitely have heavier, look, I even said heavier. Look at that mistake. Relative heaviness. They have greater densities, with gold being 19.3, lead, silver, okay? If we look, most of these solids, right, they're all more dense than water, okay? But we do see that wood and cork float. Now, when I go to liquids, they're still pretty condensed phases, right? When I think of solid, liquid, gas, the solids and the liquids have they have a fixed volume because their particles are close to one another. So the units are still for density grams per mil because they take a relatively small space to get grams. The one that I really want you to remember is water. And it's an easy one to remember. Why? Because it's one. Water at 4 degrees Celsius is 1 gram per mil. And that's just a standard. It helps you look and you see why all of these solids would sink because they have greater densities in water. And you see why cork and wood would float because their density is less than 1. Now, when I go to gases, if you look, The units are not grams per mil, they're grams per liter. And why is that? Well, now you have to get a large volume because the majority of the gas is the particles are so far from each other, it's empty space. So you have to get a really large volume to get any type of mass. Now, don't be confused. This looks like, oh, they're bigger than one, so they're more dense than water. Again, these units are liters, so it's not the case. Oxygen is not more dense than water, okay? So with density, we have to be able to calculate density, right? So what is the density of osmium, which is a very dense metal, if 50 grams of it has a volume of 2.2 centimeters cubed, right? So what could we do? Well, we could take a cube and set it on a scale and measure its mass, let's say 50 grams. And then you could use your volume formula, right? And we know volume is length times width times height. And we can measure the length, the width, and the height of this. Now to get 2.22 centimeter cubed, I mean, it would probably be, I mean, this would be something like 1.304 centimeters, and everything would be, and we would have to cube that, and we would roughly get the 2.22 centimeters cubed. But let's say we did that. So now we have a mass, and now we have a volume. All we need to do is DMV, right? So DMV, mass over volume. And I have 50 grams over 2.22 centimeters cubed. This has 3 sig figs because those zeros are, they count because there's a decimal even though they're trailing. This has 3 sig figs as well. So I'm following the rules of multiplication and division, picking the least. The least is 3. My final answer should have 3 sig figs. When I calculate this out, I get all these numbers, but if I go 1, 2, 3, and I look over to the right, I see the 2, so that means I drop it, I don't round up. My final answer is 22.5 grams per centimeter cubed, or I could have written this 22.5 grams per milliliter, because those are used interchangeably. And that would be my final answer. Correct number, correct sig figs, correct units. Now, sometimes the object cannot be measured directly. So the volume can't be measured. If you look at this cylinder, right? And if it was a perfect cylinder, you know, if it was perfect, I could measure it directly, right? I can measure the radius and I can measure the height. And I know that volume of a cylinder would be pi r squared times the height, because, you know, I would take the area of this base, which is pi r squared, and times it by the height to get the volume. I could do that. But if you look at this cylinder, it's all kind of chipped and broken. So a better way to do it is volume by displacement. So what I'll have to do is I'll have to make sure to take an initial volume, right? So my first measurement is I get an initial volume of water. I have to make sure it's a volume that's high enough in this graduated cylinder. When I put the cylinder in there, it's going to be completely submerged. So it has to be under the water level. It can't be poking above. But then once I submerge it, its volume is going to displace the liquids and raise it. So then I get a new volume, which I'll call V final, and I can figure out the volume of this cylinder by subtraction, right? Just by the difference. So I basically, my delta V, which is my V final minus V initial, will give me the volume of this cylinder. Now, if I line these up, I'm going to get 9.5. Now, a lot of people might be confused and go, wait a second, there's 3 sig figs in the volumetric measurements. Why are there only 2 for the final answer. That doesn't make sense. Well, you have to remember, right? We're subtracting, and when we subtract, we don't use the number of sig figs for the calculation. That's the multiplication and division rule. In addition and subtraction, we use the least precise measure unit, right? So we use the least precision, or I like to say we use the placement value, the least placement value. So both of these are to the tenths. So my final answer is to the tenths. I can't go over to the hundredths and add a zero because my volume, I mean, even the tenths was a doubtful digit. I can't go to the hundredths place. So I have to stop at the tenths. And it just so happens when I subtract it, I get 9.5. So this is the correct sig figs for the volume because I followed those rules. Now I would measure the mass of this cylinder, and I'm going to count that zero there. Why? Because that instrument is calculating till centigrams. So I want to include that zero because it tells me that this measurement, this scale measures as the centigrams. So I would use all of those. And that trailing zero counts because, as you can see, the arrow's pointing to that decimal. It's a trailing zero with a decimal. So this is 4 sig figs. Okay. Now I do what I did before, right? I put the mass over the volume. Now I have a new rule for sig figs. I'm doing multiplication division. I pick the least sig figs. This has 4, this has 2. 2 is less than 4. My final answer should have 2 sig figs, 7.2 grams per centimeter cubed. So that's a way to do volume by displacement. Now I would recommend doing the mass measurement first, right, before the volume. That way, you know, your cylinder is dry, it's not wet. They also have this on a weighing tray. You would have to first sit the weighing tray on the scale and zero it out, then add the cylinder, right? That's also referred to as tarry. So you would tarry out the cylinder or the weighing tray, sorry. You would zero this out, the tray, and then add the cylinder. But I would do it before I submerge it in water so it's not wet and it doesn't have additional mass. I mean, you could always dry it out, but why not just first take the mass measurement and then go back to your desktop, put a certain amount of liquid in the graduated cylinder, and then submerge it. So here's another example of what we just did. Now this is volume by displacement. What is the density? So I'm looking for density. They're telling me I want density. And density is a ratio, mass, DMV, over volume, of 48 grams of metal. I already got the mass. It's 48 grams. What do I need? I need to get the volume. So what is the density of 48 grams of a metal if the level of water in the graduated cylinder rises from 25 mils to 33 mils after the metal is added? So we have it at 25 mils. We add the metal. It ends up at 33 mils. What am I going to do? I'm going to figure out the volume by what? The difference. And I could even write this, you know, in here, 33.0 minus 25.0, and I get 8 mils. So again, I'm only going to the tenths. So because of the subtraction, I'm following that rule, and I have 8.0 mils on the bottom. So that's 2 sig figs. And if I look, the 48 divided by 8 gives me 2 sig figs. So my final answer is 6 grams per centimeter cubed. Now, both of these problems that we've done, we're using density in a formula method, right? We first did by direct method where you can measure the lengths of a perfect cube. Then we did it by displacement. But what about density as a conversion factor? This is where density is actually really useful, and it goes back to problem solving using conversion factor method. So in this particular example, it says the density of a substance is 3.8 grams per mil. Well, what does that mean? Well, I could put it in a ratio and I can flip it around to solve for problems. So that's what I'm going to do in this next example. An unknown metal, so I don't know what this metal, what it is, but I do know that it has a density of 3.8 grams per centimeter cubed. How many liters are in 2.68 pounds? So if I follow my 5 basic rules that we've discussed, what do I want? That's the first thing. I want liters. What am I given? Now, people might get confused. I'm given 3.8 grams per centimeter cubed, and I'm given 2.68 pounds. Liters is not a conversion factor. It is not a ratio. If I don't end with a ratio, I don't start with a ratio. Density is a ratio. So if I start with density, I'll end with a ratio. So I'm going to start for my given, the 2.68 pounds. So that's a way to figure out which one of these am I using. Am I using density or am I using pounds? I'm using pounds because liter is not a ratio, so I can't start with the ratio. Pounds isn't a ratio, so I start with pounds. And now if I look, well, I know I can convert pounds, so this is where I kind of got to figure out, well, what do I do? What do I do? I can convert pounds to grams, right? So I can do my download dump, right? I know in 1 pound, there's 454 grams. So that allows me to go from pounds to grams. And then from grams, using density, which is a conversion factor, I could go to, right, centimeter cubed. How come? There's 3.8 grams in 1 centimeter cubed. And now I know, right, I can go to liters because there's 1,000 centimeters cubed, because a centimeter cubed is a milliliter, in 1 liter. So that's kind of the download dump and setting up the path. That's the hard part with problem solving. Usually it takes students a while to do it. Once it clicks, but you are going to have to work to get it to click. And the only way to do that is by practicing problems. So here's my setup, 2.68 pounds, right? And I see that the pounds cancel, I'm left with grams. The grams cancel, I'm left with centimeter cubed. And in this example, if you want, you can do an extra step and say, well, 1 centimeter cubed is 1 milliliter, and there's 1,000 mils in 1 liter. And that's what I want. Or you could do the shortcut that I did. So my final answer is 0.32 liters. Now, why 0.32? Well, in the actual problem, I'm given 2 numbers. The 3.8 grams per centimeter cubed for density, that's 2 sig figs. 2.68 pounds, that's 3 sig figs. So what's less? Because all of this is multiplication and division. 2 sig figs is smaller. So my final answer should be 2 sig figs. Now remember, we're treating these conversion factors that we bring in as exact. We're not using them for sig figs. We are using the density because it was provided in the problem and it's a measured value. So my final answer should have 2 sig figs, not 3. This 0 does not count. Why? It's a leading 0. It's to the left of the non-zero digits, and leading zeros never count. So I hope this helps you with understanding density, what exactly it is, how to calculate it, and how to use it as a conversion factor in word problems, and going back and revisiting the 5 basic rules or strategies for solving these word problems. Thanks for listening. If you have any questions, go ahead and put them on the discussion board, write them in your comments, or go ahead and send me an email. Thanks.